Hi everyone, welcome back to session 5 on quantitative methods in management. Now in the last session, we had seen the various types of OR models, standard formulation of linear programming problem, and we just started off with the first exercise on formulation of LPP. Now we will continue with that exercise and do a few more problems in today's session. Let's get started. Now to have an overview of what we studied, we are just seeing this standard formulation of linear programming problem, which consisted of three elements basically. One is identification of the decision variables in the problem, which are represented as x1, x2, x3, etc. up to xn, which will have positive or zero values, meaning it is always non-negative. And then we have the objective function, which needs to be maximized or minimized in the problem, which needs to be optimized, which is given as an expression in terms of the decision variables as maximization or minimization of the function z, which is equal to c1 x1 plus c2 x2 etc. up to cn xn. So n can be 2, 5, 10 and so on. Now here in this objective function, C1, C2, C3, etc. indicate the unit cost or unit profit of the decision variables, depending on whether it is minimization or maximization. Now this objective function is valid only if it satisfies the constraints of the problems. So the constraints indicate resources which may be available or which may be required for satisfying the problem. So the constraints are expressed as a11x1 plus a12x2 plus a13x3 etc. up to a1n which with the inequalities which may be of the form less than equal to or greater than equal to or equal to the constant b1. Similarly, it can be up to mth equation am1 x1 plus am2 x2 plus am3 x3 etc. up to amn xn less than equal to or greater than equal to or equal to bm. In this equation, a1, a2 etc. up to bm indicate the available resources or required resources for the problem. And a1, a11, a12 etc. up to a1n and amn indicate the unit resources required for each of the decision variables. So these equations are indicated as constraint equations. So basically three elements are required. The decision variables whose values we need to identify are determined by solving the problem, and by substituting the values of the decision variable we try to optimize the objective function, which may be of the form maximization or minimization, which will be valid only if the constraints or restrictions of the problem are being satisfied. Now let's move on to an example which we already discussed. So this was the first example which saw in the previous session. We just started off with the example. So we'll just briefly see what is this example. So there was this example deals with an industry manufacturing two types of cements, namely A and B, and each of the types of cement are being sold for rupees 50 per unit of A and rupees 65 per unit of B. So the profit per unit of A is rupees 50 and profit per unit of B is rupees 65. And each of these types of cement are required to be processed on two machines R and S. And the requirement of each of the machines are given here. Type A cement 1 unit requires 1.5 hours of processing time on machine R and 2.5 hours on machine S. Similarly, the requirement for 1 unit of cement B is 2 hours and 3 hours respectively for processing on R and S. The availability of each of the machines are given. Machine R is available for not more than 6 hours and 40 minutes per day. Similarly, machine S is available for 10 hours and 20 minutes only on each day. Now they have asked us to formulate the problem as a linear programming problem. So we have to use the standard formulation steps for formulating the problem into a mathematical model. So let's proceed. So first, to start with, we are expressing the data given in the statement problem into a table. So the table is like this. So table contains the cement, which is A and B. Two types of cements are being manufactured in the cement industry, which are A and B. So they are written in two columns like this, and each of the cement require processing on two types of machines. One is rotary kiln and grinding machine, and their requirement for 1 unit are given here. Okay, that is, machine A is being processed on a rotary kiln for 1.5 hour. 1 unit of machine A requires 1.5 hours of processing on rotary kiln, and machine B requires 2 hours of processing on machine R. Similarly, machine A requires 2.5 hours of processing on machine S, and cement A requires processing 2.5 hours of processing on machine S, and cement B requires 3 hours of processing on machine S. So their their availability of each of the machines are given on the right extreme. That is, machine R is available for not more than 6 hours and 40 minutes per day. Similarly, machine S is available not more than 10 hours 20 minutes per day. And profit per unit of by selling each of the units of A and each of the unit of B is given to us as rupees 50 and rupees 65. So the first step is to identify what are the decision variables in the problem, so which can be seen by the cement A and B. So the manufacturing industry will be interested to know how many units of type A cement to be manufactured per day and how many units of type B cement to be manufactured per day. So these two are the decision variables in the problem. That is, let us take x1 to be number of units of cement A to be manufactured per day and x2 to be number of units of cement B to be manufactured per day. So we have identified what are the decision variables, and its values we have to solve while solving the problem using any of the techniques. Then we have to proceed to the objective function. So objective function is maximization, because the hint here is profit per unit is given to us, meaning that we need to maximize the profit by selling x1 units of A per day and x2 units of B per day. So our objective function is going to be maximization of Z is equal to C1 x1 plus C2 x2, where C1 indicates the unit profit by selling 1 unit of A, which is rupees 50, and C2 indicates per unit profit of selling 1 unit of B, which is 65 rupees given in the problem. So with this we can write the expression with the original data that is given in the problem. So our objective function becomes maximization of Z is equal to 50 into x1, meaning by selling 1 unit of A, I am able to get a profit of 50 rupees, and I am going to manufacture x1 units of A. That means the total profit that I will get by manufacturing x1 units of A is 50 into x1. Similarly, by selling 1 unit of cement B, I will be producing 65 rupees as profit. I am going to manufacture x2 units per day. Therefore, my total profit with respect to B will be 65 into x2. So my total profit of the company per day would be 50x1 plus 65x2, because I am manufacturing two products A and B. So their total profit is going to be 50x1 plus 65x2, which is the objective function. Now this objective function is valid when it is subject to or satisfies the constraints in the problem. So two constraints are given to us in the problem. One is with respect to machine time of R and machine time of S. So R indicates rotary kiln and S indicates grinder. So machine time of R S can be expressed as A11 x1 plus A12 x2 should be less than or equal to the availability, because our available machine time per day is not to exceed 6 hours 40 minutes, meaning that the available whatever we manufacture should be less than or equal to 6 hours plus 6 hours 40 minutes. That is the appropriate type of constraint. So we have any of these inequalities can be used, either less than equal to or greater than equal to or equal to. Appropriately we have to use inequality depending on the constraint given in the problem. Okay, so here we can see that the machine time is restricted to 6 hours and 40 minutes for R and 10 hours and 20 minutes for B. So whatever we produce with respect to A and B should be less than or equal to 6 hours and 40 minutes with respect to R and 10 hours and 20 minutes with respect to S. So these two can be written as 1.5 x1 plus 2 into x2 less than equal to 6 hours 40 minutes, and with respect to x, the second constraint will be 2.5 x1 plus 3 x2 less than equal to 10 hours 20 minutes. So you can see the equations like this. So restriction on rotary kiln availability is 1.5 x1 plus 2 x2 less than equal to 6.67 hours. So please remember here we have to use constant units on either side of the equation. So left hand side the values are in hours, therefore right hand side I am converting everything into hours. 6 hours 40 minutes has been converted as 6.67 hours. Similarly, the restriction on grinding machine time availability can be written as 2.5 x1 plus 3 x2 less than equal to 10.33 hours. So these two are the constraints. Finally, we have the non-negativity constraint, which is x1 plus x2 greater than equal to 0. So this is how we formulate the problem. Thank you, students.